now we consider a uniformly charged line of charge, so that the charge is distributed over a straight line, a portion of the x-axis, and it is uniformly distributed there. And I want to find the electric potential at a point along the y-axis. So it is this, like, think of it this way. You have this portion of the x-axis carries a charge q that is uniformly distributed over it, and the length of this portion is L, and so that the charge density here, which is the linear charge density, is the total charge divided by length, so it's Q over L coulombs per meter. So this is the charge that is distributed on the line, and I want to find the potential at an arbitrary point along the y-axis at a distance a from the origin. So one end of the line is at the origin, the other end is at x equals L, and I want to find the potential at a point along the y-axis at a distance a from the origin. Okay, so this is my configuration, and that I want to find the potential for. Well, we proceed as usual. First of all, identify a given dq here, which sits over a unit which is distributed, or which occupies a length equal dx. This distance to the origin is x. This is the corresponding r for this dq, and evidently from here r is equal square root of x square plus a square, as you can see here from Pythagoras theorem. And this dq is nothing but lambda dx, because it has a length dx, and so the charge density is lambda, which is charge per unit length, so it's lambda dx. This is the charge on this dx. So after I do these analysis, I apply the routine, which is, or the algorithm, which is first find dv. So I write down my dv, which is k dq over r, as usual. Substitute for r from the geometry, okay, from the dimensions or for the lengths given in the problem. So adapt r to the situation given in the problem. Substitute for dq in terms of the charge density, and if you do this, this k becomes dq here is nothing but lambda dx, and the r below is just x square plus a square. So this is your dv. Now once you write this down, especially as always, I always said, once you express dq in terms of the charge density, you get a hint of what's your integration variable. L is, it seems that x is my integration variable. The second thing, I have to identify this, then you find v is just dv. You add up all the contributions from all dq's, which means you integrate over dv. And if you go here, you can see that k and lambda are just constants, so the integral is dx over square root of x square plus a square. And now what remains is to identify what are the limits of your integration. Now, when I add all the integration variable is evidently the x. So x varies from where to where over the charge distribution. Evidently x varies from 0 to L. This is the range of x that is covered by, or that is occupied by, the charge. Okay, so it is from 0 to L. You also make a physical check saying that if I really integrate over x from 0 to L, do I really catch all the contributions of the dq's that form for me this charge? The answer is yes, because all of these dq's, when you add them up together to find their potentials here, you actually, x varies from this point, which is 0, to x equals L. So physically, actually, when you are integrating from 0 to L, you are catching the contribution of all these, the dVs of each of these dQs. So things are now make sense physically, and it seems that we are on the right track. Now what remains? The physics is over here, actually. Most of the physics, 90% of the physics is done. Once you write down this integral, what remains is to calculate, find the value of this integration, or integrate, and then substitute the limits. Well, this is a standard integral, and the result is a logarithm. So len, so k lambda len x plus square root of x square plus a square between 0 and L in this case. And if you do this, this becomes k lambda len, you substitute L, so L plus square root of L square plus a square minus, when you substitute 0, this is 0, this becomes just a, and this becomes, V becomes k lambda len L plus square root of L square, this is a square, plus a square divided by a. So this is my expression for the potential of this line of charge at the point A. Now we can check the limits, the dimensions, the units, to see that we don't have at least a mistake, because if you having right units does not mean you have the right answer, but having wrong units means that you definitely have a wrong answer. So the logarithm is dimensionless. There are no units here, but length over length. If you look here, k lambda, well, lambda you can express it as q over L, so you can write this as k q over L len L plus square root of L square plus a square divided by a, and write it this way. Now this has the units of, k multiplied by charge divided by length, which is exactly the form for a potential. So there is no, the expression is right dimensionally.